Welcome to this exciting exploration of large language models, a revolutionary technology reshaping the way machines understand and interact with human language. We'll begin by introducing large language models, what they are, how they work, and why they are transforming industries worldwide. It has an incredible architecture rooted in transformers, which has revolutionized how language models operate. We'll break down the key components of this architecture, starting with attention mechanisms, which allow the model to selectively focus on relevant parts of a sentence, mimicking human attention. You'll also dive into the roles of encoders and decoders, the backbones of LLMs, understanding how one interprets the input and the other generates coherent, fluent outputs. We'll also explore the key query value mechanisms, a critical aspect of how these models determine what information is most important. From there, we'll explore real world applications of LLMs, revealing how they power chatbots, content generation, translation tools, and even help businesses make data driven decisions. But behind the magic, there is a deep dive into the technologies behind LLMs and the significant hardware requirements needed to train and optimize these models for peak performance. Our journey doesn't stop there. We'll look at the objectives behind using LLMs, where prompt engineering, the art of crafting effective inputs, plays a key role in achieving desired outcomes, and of course, evaluating LLM performance is crucial to ensure models are meeting expectations in real world scenarios. Finally, we'll wrap up with a look toward the future of LLMs and their continuing advancements. So, get ready to demystify LLMs and discover how they are shaping the future of AI driven language understanding. Let's dive into the nature of LLMs. These models are incredibly sophisticated AI systems that harness vast amounts of data to understand and articulate human language fluently. Think of them as expert linguists. They have observed extensive knowledge and can respond in ways that feel natural and intuitive. LLMs have diverse applications across many fields. They are not just about generating text. They can summarize information, translate languages, and assist with tasks that boost productivity in areas like customer service, content creation, and even technical writing. To make this clearer, imagine LLMs as scholars. Just like a well read scholar synthesizes knowledge to hold conversations, these models process information to engage in dialogue, making them powerful tools for facilitated human like interactions. Transformers have been a game changer in the field of natural language processing since their introduction by Vaswani in 2017. Before Transformers, models like RNNs and LSTMs struggled with processing long sequences due to their sequential nature. So, what makes Transformers so special? Parallel processing. Transformers process all words in a sentence simultaneously rather than one at a time. This significantly speeds up computation and allow handling longer sequences. Self attention mechanism. This enables the model to consider the context from all parts of the sequence when encoding a specific word. Scalability. Transformers can be scaled up to create larger models like GPT-3, which have billions of parameters and can capture more complex language patterns. Technical insight. Transformers rely heavily on matrix multiplication and linear algebra, which are efficiently executed on GPUs and TPUs. They replace recurrence with positional encoding to maintain the order of words, which is crucial for understanding syntax and semantics. Just think of a transformer as a team of chefs preparing a meal. Instead of one making a dish from start to finish, each chef works on their part simultaneously, resulting in a faster and more efficient cooking process. Alright, let's dive into the Transformers architecture, which is the backbone of many modern large language models. This architecture is responsible for the impressive capabilities you see in models like GPT and BERT. which can understand and generate text, perform translations, summarizes documents, and much more. The beauty of this architecture lies in how it handles language in a way that allows the model to understand complex relationships between words. In the input stage, when we feed text into a transformer, the first thing the model does is convert these words into something it can understand. That is embeddings. Think of embeddings as numerical representation of words that capture their meaning. This helps the model work with words in a more mathematical way. But there is one problem. The transformer doesn't really know the order of words since it processes them all at once. That's where positional encoding comes in. It's a clever technique that lets the model know the position of each word in a sentence. This encoding adds a bit of information to each word so that the model knows whether the word appears first, second, or at the end of the sentence. Without this, the model would have no idea if it's reading the dog chased the cat or the cat chased the dog. Now that we have got our word appended and their positions sorted, we move into encoders. The encoder is like the brain of the transformer. It's made up of multiple layers and each layer has two parts, self-attention and feed-forward network. Let's break this down. The self-attention mechanism is a magic sauce. It allows the model to focus on certain words in a sentence based on their relevance to others. For example, in the sentence, the dog chased the cat and it ran fast. The word it could refer to either the dog or cat. The self attention mechanism helps the model figure out that it refers to the cat because it weighs the relationship between all the words in the sentence. Here's how it works. Each word creates three vectors: a query, a key, and a value. These vectors help the model figure out how much attention each word should pay to the others. For every word, the model compares its query to the keys of other words to compute attention scores. Then it uses these scores to create a weighted average of the values. This lets the model focus on important words while downplaying less relevant words. Once the attention mechanism has done its job, the model moves the information through a feed-forward network. This is where the real processing happens. The feed-forward neural network applies transformation to the data, making it easier for the model to understand complex relationships between the words. This part helps the model understand patterns that go beyond the simple attention mechanism. One of the cool things about transformer is that they don't just compute attention once. They use something called multi-head attention. Basically, instead of having one attention mechanism, the model has multiple heads that each focus on different aspects of the relationships between words. This allows the model to see the sentence from different perspectives, like human thinking about a sentence from different angles. Each attention head captures unique aspects of the meaning and they all come together to give a richer understanding. Now, let's move to the decode side, which is where the magic happens in terms of generating output. Whether it's producing the next word in a sentence or translating text, the decoder has similar structure to the encoder but with a key difference. Like the encoder and the decoder has the self-attention mechanisms and feed-forward networks. However, the decoder also has a layer called encoder-decoder attention, which allows it to look back at the input from the encoder. This is particularly useful when the model is generating translations or responses. It can refer to the original input sentences while generating the output. When the decoder is generating words, it can't cheat and look at future words, so we use something called masked self-attention. This ensures that when the model is predicting the next word, it only considers the word it's already generated and doesn't peek at the rest of the output. The encoder. Input appending and positional encoding are key aspects here. We start by feeding a sequence of inputs, let's call them words or tokens, into the encoder. Each input gets converted into appendings with fixed vector representations, which also include positional encoding to preserve the order of words. Since transformers don't have recurrence like RNNs, this step is crucial for maintaining sequence information. Self-attention mechanism is inside the encoder block. The appending input passes through the self-attention layers where each word in the input looks at every other word in the sequence. This allows the model to focus on different parts of the sequence depending on the context. The self attention block consists of three components: query, key, and value. The mechanism compares the query of each word with the keys of other words to decide how much attention to pay to each part of the sequence, and then it weighs the values accordingly. The input goes through multiple encoder layers, and this example shows encoder 1 through encoder 4. Each layer repeats the same structure, that is, embeddings plus self attention, gradually refining the representation of the input sequence. Once the final encoding is completed, the last encoder layer produces an output. In this example, it is shown as encoder 4 output. In the diagram, this output is a processed representation of the input sequence ready to be passed to the decoder. On the right side, we have the decoder output embedding and positional encoding. On the decoder side, we feed the output sequence. For example, in machine translation, this would be the words in the target language. In the similar way as this input sequence, like the encoder, each token in the output sequence gets embedded and positional encodings are added to maintain the order. And the decoder has a self attention block, but it operates differently. The self attention layer only looks at the previous tokens in the output sequence, because when generating text, it shouldn't see future tokens. And in encoder and decoder attention, this is a crucial block where the decoder interacts with the encoder output. Here, the decoder attends to all positions in the encoder output, effectively looking at the entire input sequence to help predict the next token. This allows the decoder to focus on specific parts of the input sequence while generating each token in the output. Similarly to the encoder, there are several decoder layers, and this diagram shows the decoder 1. Each layer progressively refines its understanding of the input sequence by looking at both the decoder's self attention output and the encoder output. In summary, the encoder processes the input sequence using multiple layers of self attention, refining its understanding at each step. The decoder, in turn, takes both the previous output sequence and the encoder's output, using this combined information to generate the next word in the sequence. The key idea behind the transformer is attention, both in the form of self attention within the input or output sequence and cross attention, where the decoder looks at the encoder's output. This architecture allows transformers to handle complex tasks such as machine translation or text generation efficiently and with a deeper understanding of context compared to older models. Let's talk about the attention mechanism, the heart of the transformer architecture. It's the feature that makes these models so powerful at understanding language. At its core, the attention mechanism allows the model to focus on the most important words in a sentence while processing it. Think of it as model's ability to ask which parts of the sentence really matter for understanding the meaning. And how does it work? It works by relevant scoring. For every word in the sentence, the model calculates a relevant score to understand how much attention it should pay to other words. For example, in the sentence, the dog chased the cat and it ran fast, the word it could refer to either the dog or the cat. The attention mechanism helps the model figure out that it is more likely referring to the cat by analyzing the context and contextual relationships. Words don't exist in isolation. Their meanings depend on the words around them. The attention mechanism captures these relationships dynamically, ensuring the model understands the bigger picture. And dynamic focus, just like how we shift our focus when reading a complex sentence, the model dynamically adjusts its attention. It gives more weight to important words and less to irrelevant ones. Technically, here's how it works. Each word generates three vectors: query, key, and value. The model calculates the relevance of a word by comparing its query to the keys of other words. This comparison, done through a dot product, gives us attention scores. These attention scores are normalized using a softmax function to ensure they add up to 1, and then they are used to compute a weighted sum of the values. This weighted sum lets the model focus on more important words while minimizing noise from irrelevant ones. This mechanism is what makes Transformer excel at tasks like translation, summarization, and querying answers. It gives the model the ability to understand context and relationships between words, even in long or complex sentences. Without it, handling nuanced language could be clearly impossible. In short, the attention mechanism enables the model to think more like us, focusing on what matters and understanding relationships within language. Let's dive into the encoders, the first half of the transformer architecture. Their job is to thoroughly read and understand the input data. You can think of them as meticulous readers who not only look at the words but also grasp the deeper themes and relationships within the text. What do encoders do? The first thing the encoder does is to convert words into numerical vectors using embeddings. These vectors capture the meaning of words in a way that the model can understand. And by contextual encoding, words doesn't mean much as their own. They need context. The encoders uses self-attention to analyze relationships between words and understand how each word influences the other. And by generating encoded output, the encoder finally produces a set of vectors that encapsulate the meaning of the entire input sequence, and this encoded output is ready to be passed to the decoder for generating the final result. And how does it work? Encoders are made up of multiple layers, and each layer has two key components. Multi-head self-attention mechanism. This helps the encoder focus on different parts of the input sequence simultaneously, capturing multiple perspectives of the relationship between the words. And position phase feed-forward neural network. Once the self-attention mechanism has done its job, the network processes the information further, identifying complex patterns and the refining the representation of the input. To ensure everything runs smoothly, encoders use layer normalization, which keeps the training stable by standardizing the outputs at each step. Residual connections. These connections help the model retain important information as it moves through layers. In short, the encoders transform raw input into a meaningful structured representation that the decoder can use to generate accurate and context aware output. Let's shift our focus to the decoder, the second half of the transformer architecture. If the encoder is like skilled reader, the decoder is the storyteller, taking the understanding provided by the encoder and turning into a meaningful, coherent output. What do decoders do? Decoder starts by taking the encoded representation from the encoder. These are rich, contextualized vectors that represented the input sequence. Using this information, the decoder predicts the next word in the sequence one step at a time. For example, in a translation task, it generates each word of the translated sentence, and it maintains coherence. The decoder ensures that the output isn't just grammatically correct but also contextually appropriate. It draws on the encoder's understanding to make sure the narrative flows naturally. The decoder, like the encoder, has multiple layers, and each layer has two key components. Masked multi-head self-attention. This mechanism ensures the decoder focuses only on the words it has already generated without cheating by looking at future words. It's like a storyteller who crafts the narrative one word at a time without skipping ahead. Encoder and decoder attention is where the magic happens. The decoder refers back to the encoded representation from the encoder to decide which parts of the input sequence are more relevant for generating each word. Additionally, residual connections and layer normalizations are used here as well, ensuring stability and efficient training. Now let's take a closer look at key query and value mechanism, a fundamental concept in how attention works within transformers. Here, the query represents the current word the model is focusing on in the output, and the key represents all the words in the input sequence, and the value holds the actual information associated with those input words. And for calculating scores, for every query, the model computes a similarity score with all keys using dot product. This tells the model how relevant each word is to the current focus. And for determining weights, these scores are passed through a softmax function, converting them into probabilities that add up to 1. For computing the weighted sum, the probabilities are multiplied by the corresponding values and the result are summed to produce the output. This process allows the model to dynamically focus on the most important parts of the input sequence while generating each part of the output. It's what enables transformers to handle complex relationships in language, improving tasks like translation and context understanding. And that's the essence of the key query and value mechanism, the backbone of attention in transformers. Building and deploying LLMs require a robust set of technologies. Programming languages: Python, the go to language due to its simplicity and extensive libraries. Frameworks like TensorFlow, which provides a comprehensive ecosystem for machine learning development, and PyTorch, which is known for its dynamic computation graph and ease of use in research. Libraries like Hugging Face Transformers offer pre-trained models and tools accelerating the development. NumPy and SciPy are used for numerical computations, and for development environments, Jupyter notebooks, which are ideal for interactive coding and visualization, and integrated development environments like PyCharm or VS Code for efficient coding. Version control like Git and GitHub are essential for collaboration and tracking changes. The contribution of these each tool are very important. Frameworks and libraries handle the heavy lifting of model training and optimization, and development environments facilitate experimentation and rapid prototyping, and version control ensures code integrity and collaboration among team members. These technologies are the toolbox of a craftsman, each tool serving a specific purpose to build a masterpiece. Training and deploying large language models effectively requires robust hardware capabilities to handle computational demands. Essential components include CPUs, GPUs, and TPUs, each serving specific roles in the process. CPUs are versatile and ideal for general purpose computation, but they lack the parallelism required for large scale training tasks. So, GPUs, on the other hand, excel at parallel processing, making them well suited for the massive matrix operations that LLMs demand. TPUs, custom designed by Google, provides specialized acceleration for machine learning workloads and often outperform GPUs in specific tasks with greater energy and efficiency. Utilizing high performance computing offers significant benefits, including faster training times, reducing weeks of computations to days or even hours, and enhanced inference capabilities for real time applications. A comparative analysis of hardware capabilities revealed that while CPUs are limited in parallelism and suited for smaller tasks, GPUs offer high parallelism for training and inference, and TPUs provide a specialized architecture that optimizes machine learning workflows. Choosing the right hardware ensures efficient training and deployment, making it a crucial factor in unlocking the full potential of LLMs. For optimizing LLM performance, fine-tuning large language models involves leveraging domain-specific datasets to refine their understanding, enabling them to excel in targeted tasks and deliver superior results. This process tailors the pre-trained model's knowledge to specific use cases, improving accuracy and relevance. Additionally, hyperparameter optimization plays a critical role in enhancing performance by systematically fine-tuning key parameters such as learning rates, batch size, and network configuration. This careful adjustment can significantly boost model accuracy and efficiency. To maintain robustness and adaptability, continuous evaluation is essential. Regular performance assessments provide valuable insights, ensuring the model remains effective and highlighting areas for iterative improvement. Together, these strategies enable LLMs to reach full potential in dynamic and specialized environments. The objectives behind utilizing large language models can be categorized into short term and long term goals, each contributing to their transformative potential across industries. In the short term, LLMs aim to enhance linguistic understanding and optimize efficiency for specific applications such as text summarization, translation, and conversational AI. These immediate goals focus on refining the model's performance in targeted tasks to deliver precise and efficient solutions. Looking towards the long term, the aspirations are more ambitious. The objective is to achieve a broader contextual comprehension, enabling LLMs to grasp and generate complex, nuanced content across diverse scenarios. The development of highly adaptable models that can seamlessly transition between domains without significant retraining is a key focus. The expected benefits of deploying LLMs are substantial. They drive increased productivity by automating and streamlined workflows, accelerate innovation by enabling cutting edge applications, and enhance user experiences through intuitive and context aware interactions. Together, these objectives and benefits position LLMs as important tools for advancing technology and solving complex challenges across industries. Prompt engineering is a critical skill for effective leveraging large language models. The way prompts are crafted directly impacts the quality of the model's output as they guide the model toward producing accurate and relevant responses. A well constructed prompt provides clear direction, ensuring that the generated answers align with the intended goal. To create effective prompts, it's essential to focus on clarity, specificity, and context. Clear prompts minimize ambiguity, reducing the likelihood of irrelevant or confusing responses. Specificity helps narrow the scope of the output, leading to precise and targeted answers. Additionally, providing context allows the model to better understand the task at hand, enabling it to generate more relevant and coherent responses. For example, a vague prompt like explain transformers may result in broad and generic response. In contrast, a detailed prompt such as explain how transformers work in natural language processing, focusing on the role of attention mechanisms, yield a more structured and contextual relevant explanation. These examples demonstrate the importance of carefully formulating queries to achieve high quality outputs. By mastering the art of prompt engineering, users can fully harness the potential of LLMs, ensuring their outputs are precise, coherent, and tailored to specific needs. Evaluating the performance of large language models requires robust metrics to quantitatively assess their effectiveness across different tasks and applications. Key metrics such as perplexity, accuracy, and F1 square provide insights into the model's capability in language generation, classification, and retrieval tasks. Perplexity is a critical metric for language generation tasks, measuring the model's uncertainty in predicting the next word in a sequence. A lower perplexity score indicates better predictive capability, specifying that the model is more confident and accurate in its prediction. For classification and retrieval context, the F1 score becomes essential as its balance precision, the portion of relevant results among the retrieved items, and the recall, the portion of relevant results successfully retrieved. These make the F1 score particularly relevant for assessing the accuracy and completeness of model prediction. In machine translation tasks, the blue score is commonly used. It evaluates the quality of machine generated text by comparing it against one or more reference translations, measuring how closely the output matches human like translations. For summarization tasks, the Rouge score is preferred metric, quantifying the overlap between machine generated summaries and reference summaries by comparing n-grams, sequences, or word pairs. These evaluation metrics collectively provide a comprehensive view of a LLM's performance, enabling developers to fine tune models and optimize their effectiveness for specific applications. In this video, we have explored how large language models work, their real world applications, and the impact they are having across different industries. These models have huge potential to change the way we generate text, translate languages, and summarize information, making tasks easier and more efficient. Looking ahead, LLMs are only going to get better. They'll understand context more deeply and become a natural part of everyday technologies, helping us interact with tools and devices in smarter, simpler ways. This progress will open up new possibilities and bring big changes to how we live and work. Thank you for watching and being part of this journey into the world of LLMs. The future is bright, and we are excited to see how these powerful models will shape our world.